Hi, my name is Tej, and I'm going to talk about Perennial, a framework we built for verifying concurrent storage systems. Many systems need concurrency and crash safety. Examples include file systems, databases, and key value stores. All of these systems make strong guarantees about keeping your data safe, even in the presence of crashes, for example, due to power failures or kernel panics. At the same time, they achieve high performance using concurrency. The combination of these crash safety guarantees and concurrency in the implementation makes these systems difficult to make correct. As a simple motivating example of a concurrent crash-safe system, consider a replicated disk. This is a system that replicates writes across two unreliable disks. It exports a simple read-write interface on top of a single logical, and behaves like a single logical disk. But in the implementation, it handles fail-stop failures of one of the underlying disks at any time. And also, it handles crashes of the entire computer at any time. Even this simple system is subtle. So if we look at just the implementation of the write operation, what it does is it acquires a per-address lock, and then inside a critical section, it writes to the two disks in turn, to the first and then the second. Already some issues arise. What if the system crashes between writing to the first disk and the second? We've left the system in an inconsistent state. What if the first disk fails at some point? To solve the first problem, we run a recovery procedure on reboot, which copies from the first disk to the second. This recovery procedure completes these write operations and restores the synchronization of the two disks. To address the second issue, in the read implementation, we're very careful, and we also run this inside a critical section, acquiring the same per-address lock. This ensures that reads don't observe these writes which haven't yet made it fully to both disks. Reads always observe writes that are durable. And these are just a handful of examples of subtleties in this system. Ideally, we'd like to be able to systematically reason about all the executions of this code. And the approach that we take to do that is to use formal verification. Of course, there are existing verification frameworks, but none of the existing verification frameworks support this combination of concurrency and crash safety. And it turns out that combining verification of crash safety into a concurrency framework is challenging. There are several challenges that arise. The first is that crashes and recovery can interrupt a critical section. So usually when you're doing concurrent reasoning, you sort of assume that other threads can't run during a critical section. But crashes violate this. Crashes and recovery can totally interrupt a critical section at any time. Second, crashes wipe the in-memory state of the entire system in all the threads simultaneously. And this is not something that a concurrency reasoning framework is set up to handle. Finally, recovery can logically complete crash threads operations, which is something that we saw in the example of the replicated disk. Recovery completes these write operations. So the system that we wrote is called Perennial. Perennial introduces three techniques to address these challenges of integrating crash safety into concurrency reasoning. Our techniques are Lisa's memory versioning and recovery helping. See the paper for the details on the first two, but in this talk, I'm going to focus on recovery helping, and specifically recovery helping in the context of the replicated disk. So our contributions in this work are threefold. First, we introduced Perennial, the first framework that supports reasoning about crash safety and concurrency simultaneously, and it implements those three techniques. Next, we implemented a system called Goose, which lets us reason about Go implementations using Perennial. And finally, we have an evaluation, which includes a verified mail server, which is written in Go and verified in Perennial. And this mail server has concurrency and crash safety. So before we can talk about Perennial's techniques, we first need a specification. The specification that Perennial uses for its systems is something we introduced called concurrent recovery refinement. When a system satisfies this property, then all operations are correct. Operations return the expected values, and they're all atomic with respect to both concurrency and crashes. And the way that we achieve the atomicity, in particular with respect to crashes, is that recovery repairs the system after a reboot and completes these half-completed operations. So now we'll talk about Perennial's techniques in more detail, and I'll do this in the context of proving the replicated disk correct. Along the way, we'll see how recovery helping works as part of this proof. We start with a classic idea of forward simulation to prove concurrent recovery refinement. In forward simulation, the first thing the developer has to do is relate the states of the code and the specification. In the case of the replicated disk, the code state includes the blocks on both unreliable disks, whether or not the disks have failed, and the state of the per address locks, whether or not each address is locked at the current instance in time. The state of the specification is much simpler. It's just a single logical disk, just disk blocks. Next, in forward simulation, the developer proves that every operation has a commit point somewhere in its execution. So here I'm just showing the execution of the write operation, and it turns out that the commit point in the write is when the second write makes it to disk. At that point, the system transitions from one logical state to the next. And finally, importantly for forward simulation, the developer has to prove that the abstraction relation is preserved at all intermediate points in time as well. This is important for concurrency because at any time, another thread could start running in the middle of this write procedure. It could interrupt the write procedure, and it's also relying on the abstraction relation. So it's important that the developer proves that the abstraction relation holds at all intermediate points. So what is this abstraction relation I'm talking about? For the replicated disk, this simple abstraction relation suffices to prove that the system is correct. What it says is that if, at a given address, if it's not locked, if we're outside of a critical section, then the logical state of the system matches both underlying unreliable disks. And this is only true if the disks haven't failed. If a disk fails, then the logical state just matches the other disk, the one that hasn't failed. Now, this abstraction relation is sufficient to prove the replicated disk correct if we only had concurrency. But unfortunately, crashes break this abstraction relation. Here's the problematic case. If we crash in the middle of a write operation, and we've updated the first disk but not the second, then the crash wipes out all the state of the system, and so we lose the lock, but we haven't synchronized the disks. So this abstraction relation no longer holds. So far in forward simulation, we've mandated that the abstraction relation has to always hold, but we've seen that crashes break this property. The way Perennial solves this problem is we separate a crash invariant from the abstraction relation. So the developer, instead of proving the abstraction relation holds at every crash point, they prove this weaker property of a crash invariant, which will hold after any crash in the system. Then, the recovery proof can rely on the crash invariant holding when it starts running, and the job of the recovery procedure is to restore the abstraction relation by the time it finishes. With the abstraction relations restored, we can continue running normal operations in the system. Now, returning to the replicated disk, we want to prove that this recovery procedure is correct. And the role of the recovery procedure in this particular system is to make writes operations atomic. Writes before the crash should become atomic due to recovery. So to illustrate how recovery makes writes atomic, I'll illustrate with a simple example of what the execution looks like. I'm going to use this hourglass figure to represent a pending spec operation. This is an operation that the user has issued, which may or may not have completed at this point. So when the user first issues this write operation, in the case we're interested in, the first write to the disk makes it before the crash, but the second write doesn't. Instead, that write happens during recovery. So recovery copies this disk block from the first disk to the second. At that point, as we can see, both writes have made it to disk, and so the spec operation, the user's operation, is now complete, which I'll represent with this green check mark. It's this action that we call recovery helping, because recovery has completed an operation that was started prior to the crash. That's the kind of reasoning that we want to formalize in Perennial. So just returning to the code, we've seen how this works abstractly, but we also need to prove something formal about the code. The proof needs to show that whenever recovery copies, some thread was indeed writing to disk, because that's the only reason why this is justified. Now, the only technique that I've introduced for reasoning about recovery is a crash invariant, so we're going to have to use that technique. The crash invariant that we use in Perennial for this system says if the two disks disagree at some address, then some thread must have been in the middle of writing the value that's currently on the first disk. And intuitively, this makes sense, because in general, the system maintains synchrony between the two disks, except in the middle of the write operation's critical section. So now, armed with this crash invariant, we can complete the recovery proof. The proof developer can complete this proof. If the recovery procedure indeed copies from the first disk to the second, then we can reason that the two disks must have been different, and therefore, there was some thread writing to the disk. And that justifies this recovery helping, where we complete that operation. Now, the key idea that enables this reasoning is that the crash invariant is able to refer to interrupted spec operations themselves. This is pretty cool, because by the time the recovery code actually runs, these threads have been wiped from memory and no longer exist in the system. And yet, we can still refer to them in the proof, because they were there in the past. Finally, just to wrap up the recovery proof restores the abstraction relation by completing all of the interrupted writes. In all of the figures I've shown so far, I've only had a single pending write operation, but the system is concurrent, and so in general, we could have multiple writes that were inside their critical sections at the time of a crash. The recovery code indeed covers all of these cases, it completes all of these operations, and it restores the synchrony of the two disks. And therefore, the abstraction relation holds at the end of recovery. So to summarize what I've said so far, to prove concurrent recovery refinement, the recovery proof gets to assume the crash invariant and uses it to restore the abstraction relation. The proof can refer to interrupted operations themselves, which enables this recovery helping reasoning, where recovery completes an operation that started prior to the crash. And the upshot of concurrent recovery refinement is that users of the system get correct behavior and atomicity, both with respect to concurrency and with respect to crashes. We implemented Perennial in about 9,000 lines of code in the Coq proof assistant. The Perennial framework implementation includes these three techniques of leases, memory versioning, and recovery helping. And it's implemented by extending Iris, which is an existing concurrency reasoning framework inside of Coq. The cool thing about extending Iris is that we get to reuse Iris's techniques for concurrency reasoning and only use Perennial's techniques for the crash safety aspects. To actually write runnable systems, we implement them in Goose, which is a subset of Go. Goose code is also perfectly valid Go code, so we can use the standard Go toolchain to compile it. Then we can use the Goose translator, which is a system we implemented, to import Goose into Coq for reasoning on top of Perennial. Those proofs are then carried out in Perennial, and then we can go forward. And that Goose translator is implemented in about 2,000 lines of Go code. Finally, the proofs that the developer writes in Perennial, as well as all the proofs inside the framework, are machine checked by the Coq proof assistant, which gives us confidence that we've implemented these techniques correctly and that they're sound. To evaluate Perennial, we evaluated Perennial along several axes, but in this talk, I'm going to consider just one aspect, which is a comparison of proof effort. See the paper for some evaluation of some other verified examples, which demonstrate the generality of Perennial, an evaluation of the trusted computing base of Perennial, and some discussion about bugs that Perennial's proofs catch and don't catch. The methodology that we used to compare the proof effort of Perennial is that we verified essentially the same mail server design as our prior work in CSpec from OSDI last year. So CSpec is a verification framework which supports concurrency reasoning but doesn't have any crash safety support. In both of these mail servers, users can read, deliver, and delete mail. The mail servers are implemented on top of a file system, and they use some interesting techniques, including lock-free atomic file operations. So in particular, delivers execute concurrently with all the other operations in the system without locks. And in both of these systems, we proved that the operations are atomic, but in Perennial, we also proved that they are crash safe. So that means that when you deliver mail, if the system crashes in the middle of delivery, it's either all delivered or none of it is. And if delivery returns, your mail is guaranteed to be durable. And it turns out that the Perennial mail server was actually easier to verify in Perennial, even though it also proves crash safety. So we have less lines of proof code, and it took a lot less time. So the Perennial mail server took about 2 weeks to verify, while the CSpec mail server was verified in conjunction with the framework over the course of 6 months. And that code is actually shorter. This is mainly because it's written in Go. It actually has the same functionality as the mail server in CSpec. And I think a lot of the reason why this proof was easier is because we were able to use Iris for all the concurrency reasoning, although we needed Perennial for the crash safety, including the lock-free reasoning. And the Perennial mail server really is a concurrent. It gets speed up with multiple cores. We get, this graph shows throughput increasing as we add more cores to the system. But see the paper for details on this performance experiment, as well as comparison to the other work. So, in conclusion, Perennial introduces crash safety techniques that extend concurrent verification in Iris. We implemented a system called Goose, which lets us reason about Go implementations in Perennial. And finally, we verified a Go mail server with less effort than previous work, even though we prove a stronger property, including crash safety. Our code is open source, and you can find links to both the code and the paper at this URL. And with that, I'm happy to take questions.
Go ahead. Hi, I'm Keith Smith from NetApp. Interesting stuff. Just a minor question. You have this model where you run concurrently, you crash, and then you do recovery. Can you reason about concurrency during recovery? Can I have other operations going on while my recovery routine's running?
No, so it's actually very important to the system that you can't run operations while recovery is running, because the system only guarantees the crash invariant at the time of a crash. And so during recovery, in general, the system isn't actually in a well-defined state for other operations, and only recovery is able to handle these weird intermediate states.
Mm-hmm. Okay, thank you.
I had the same question. Thank
All
you.
right, great. The answer is still the same.
I have one question regarding your assumptions on the underlying file system.
Yeah.
Right here, you verified that the mail server is crash safe, and also it's a concurrent mail server. What about the underlying file systems? What kind of assumptions you make for the file system?
Oh yeah, that's a great question. So in this particular work, we modeled we modeled crashes under the underlying file system as process crashes. So we assume that if you write to the file system, it's immediately persistent because it's already in the kernel memory. So this is an accurate model if the process crashes, but if the whole system were to crash, then the file system actually defers writing to disk, and so you would actually lose some data. In Perennial, it is possible to specify such a file system and verify the mail server on top of it, but this is just a little bit more work that we didn't do.
No more questions? Let's thank the speaker.